Welcome to Equilibria 2.3, the effect of changing conditions on equilibrium. You need to be looking at textbook pages 25 to 27 to help with this. Our lesson objectives for today are to be able to predict the effects of changes of temperature on the value of the equilibrium constant, and to understand that the value of the equilibrium constant is not affected by changes either in concentration or the addition of a catalyst. We'll start with the catalyst because that's quite straightforward. From AS level, you should already know that when you add a catalyst, it doesn't change the position of the equilibrium. All it does is mean that you get to equilibrium quicker. So because it doesn't affect the change of position of equilibrium, it only affects the speed that you get there, then Kc will be unaffected because the proportion of products to reactants is going to be exactly the same. So if we look at this expression, Kc is the concentration of the products divided by the reactants. Of course, it's not as simple as that, because you've got the various powers that you raise the concentration of the products and reactants to, depending on their stoichiometry in the equation. But for the purposes of this video, we're just going to represent it with a simple products divided by reactants, so that we can look at the factors that influence Kc. So Kc is always the same at a given temperature, and it's unaffected by the concentration of reactants or products. So what this means is, because Kc stays the same, if you increase the amount of reactants, then the amount of products is going to have to increase as well to compensate until the ratio of products to reactants is the same as it originally was. Likewise, if you reduce the products, then more reactants would have to convert to products to make the ratio the same. And this is the basis for equilibria that we talked about at AS level. So what we're going to look at now is explaining the effect of changes in temperature on Kc. And the effect depends on whether the forward reaction is exothermic or endothermic. And in order to explain this, we need to look again at our simplified expression. So Kc is products divided by the reactants, so the concentration of the products divided by the reactants. Again, it's a simplification, but we're just going to go with it for now. So what I want you to do right now is pause the video and have a go and see if you can fill this table based on your knowledge of AS level chemistry. And then unpause it when you're confident, and then I will talk you through what actually happens. So here's the completed table, and if you look at the completed table, you can see, let's look at the endothermic first. So for an endothermic reaction, we find if we decrease the temperature, then what happens is, as you know from AS level, if you decrease the temperature for an endothermic forward reaction, it's going to favour the backward reaction. So what's going to happen is that the equilibrium is going to move left because it's going to favour the reverse reaction. So if the equilibrium is moving left, then that means that we're going to have less products than we had before, and we're going to have more reactants. So you're increasing reactants and decreasing products. So that's going to mean that Kc is smaller, because remember, Kc is a representation of the concentration of the products divided by reactants. So if we've got more reactants, then we're going to have a smaller number. For our endothermic, again, if we do the opposite, if we have an increase in temperature, then that's going to favour the endothermic reaction. So the forward reaction now is going to be favoured, which means the equilibrium is going to move to the right. And if that happens, we have more products, we have less reactants, so our Kc is going to increase. So hopefully you can see where we're going with this. So if you do the opposite, you've got an exothermic reaction, then an increase in temperature is going to favour the left reaction, the backwards reaction. So the equilibrium is going to move left, we're going to have less products, more reactants, so our Kc is going to go down. Likewise, if we have an exothermic reaction and we decrease the temperature, it's going to favour the forward reaction, our equilibrium is going to move to the right, and we're going to have more products, less reactants, which means a bigger value of Kc. So to finish off now, we'll just have a general look at the Kc equation, which is the concentration of products divided by reactants. And we're just going to have a look about what the value of Kc means, because you might be asked an exam question on this. So if we have a large Kc, then if you look at that expression, that means we must have a lot of products and not as many reactants, which means the equilibrium is going to be to the right. So a large Kc means we've got a reversible reaction where the equilibrium is sitting to the right. If we have a small Kc, that means we haven't got many products and we've got lots of reactants, which means the equilibrium is going to be to the left. So what I want you to do now is just look back at the lesson objectives and make sure you've met them, and if you haven't, then you need to do something about it, whether watching the video again or looking at your textbook. So our lesson objectives were to be able to predict the effects of changes of temperature on the value of the equilibrium constant, understand that the value of equilibrium constant is not affected by changes either in concentration or the addition of a catalyst.